Okay, you just finished the lab, you go over the questions. Now we're going to kind of take some information from the lab. First off, let's go back to temperature. Temperature is basic definition. No, we don't want to say how hot or cold. By now you should be able to come up with a better definition for that. It's a measure of the average kinetic energy of the molecules of a substance. So when you talk about kinetic energy, remember that's the energy of motion. So something with a high temperature is going to have its molecules moving a lot faster than an object with a lower temperature. You have to remember that all molecules are in constant motion. Even when you look at the table in front of you, all those molecules that make up that table are constantly vibrating. If we cause their temperature to go up, they'll actually vibrate faster and faster. Now we do have our three temperature scales, Fahrenheit, Celsius, and Kelvin. Remember that Celsius is based off of water. It's boiling points, melting points. Kelvin is the absolute scale, where 0 degrees Kelvin is the absolute bottom that we can go. And then, of course, Fahrenheit is the English system that we're so used to seeing. To go from any temperature scale to the other really isn't that difficult. Let's say I want to end up in Fahrenheit here. Well, my temperature in Fahrenheit is going to equal 9/5 of my temperature in Celsius plus 32. Also, you can think about 9/5 as 1/8, so this could be equal to 1.8 my temperature in Celsius plus 32. If I want to go from Fahrenheit to Celsius, you just rearrange your equation, really. It's going to be Fahrenheit minus 32 divided by 9/5 or times 5/9. Same thing as Fahrenheit minus 32 divided by 1.8. Either way you think about it. Easiest numbers to remember is that 0 degrees Celsius is 32 degrees Fahrenheit, and 100 degrees Celsius is 212 degrees Fahrenheit. If you know those two sets of numbers, you can easily convert from one form to another. Celsius to Kelvin is very simple too, since the absolute temperature in Kelvin is just going to equal Celsius plus 273.15. So 0 degrees Celsius is equal to 273.15 Kelvin. 0 degrees Kelvin is, of course, absolute zero. That's when molecules pretty much stop moving, and you know, the laws of physics that tend to break down at that point. Now, temperature is not a measurement of heat. You have to remember that temperature is not a measurement of heat. You cannot directly measure heat, but you can look at heat if you know what's happening before and after in a situation, because heat is the transfer of energy between two substances at different temperatures. Now, looking at the zeroth and first law of thermodynamics, they tell us that any two substances that are in contact will go to the same temperature. You put your hand onto a cold window, you're going to lose heat to the window. The window is going to gain heat, warming the window up, cooling you down. And it's all about the heat transfer. It goes from the hotter object to the cooler object until they're the same temperature. Think about your body right now. I mean, you're inside this room. The room has a temperature of 70 degrees Fahrenheit. We know your internal temperature is around 98.6 degrees Fahrenheit, which means that you're hotter than the air in the room, which means you're going to give up energy to the air in the room until it gets to the same temperature. But since this room is full of so much air, it's going to take a very long time for that to happen. And so you're just going to constantly be giving up heat to the air around you. We can measure heat in joules, calories, BTU. We just can't measure it directly. We need to know before and after of a situation. But it's always heat goes from the warmer object to the colder object. There is no such thing as cold. There's a thing as heat. So when you say nothing can gain cold, something can lose heat though. So heat is the thing that we see either be gained or lost by an object. Now, a calorie is one of those units of heat energy. The BTU is the English system. Calorie is the metric system. The joule is the standard unit we will be using. But a calorie is useful because a calorie, by definition, again, based off of water, is equal to the amount of heat necessary to raise the temperature of 1 kilogram of water 1 degree Celsius. So 1 calorie gives you 1 kilogram of water increased 1 degree Celsius. Now, you know calories because of when you look at anything you eat or drink, you look at the dietary calories. That's equal to 1,000 calories or a kilocalorie. So a dietary calorie is not the same thing, but it's 1,000 times. So if you look at, let's say, a pop that has 120 calories in it, that could raise the temperature of 1 kilogram of water 120 degrees Celsius. Actually, if it has 120 dietary calories, that's 120,000 regular calories. And you think about what that can do to this, that's the energy your body uses. Now, heat can also be used to do work or can be caused by work. You think about hammering a nail into a piece of wood. As the nail goes down, frictions actually cause some energy to be transferred out into heat. If we look at conservation of energy, the change of potential energy, change of kinetic energy, and the U here is the internal energy. So that's when we're talking about heat. Whoops. That got left behind. Change of potential, change of kinetic, change internal equals 0. So if my potential energy loses it, I don't gain anything kinetic, I must have gained that as internal energy. So now we can use the law of conservation of energy to figure out how much heat was transferred between two substances. Now, in the lab that we did, the water samples were very much the same. The only thing that changed between them was the mass and probably how much the temperature changed. If we use different substances, they would have changed by different amounts. If I take a bucket of water and add so much energy to it, its temperature will change by a certain amount. If I take, let's say, a gold bar and I add the same amount of temperature, same amount of heat to it that I did to the water, its temperature will change by a different amount. Different substances react differently when heat is added to them. Some change easily, some don't. Water actually is something that doesn't change its temperature very easily. And this is why it takes so long to boil a pot of water. This is because it actually takes a lot of energy to raise the temperature of water. Now, each substance has what we call a specific heat capacity, which is a measure of the quantity of energy needed to raise the temperature of 1 kilogram substance by 1 degree Celsius. Now, this equation here is going to be a very important equation for us starting out. Q equals mc delta T. Q, in this case, pretty much is going to be equal to the heat added, the energy transferred in joules. M is the mass of water in grams. C, specific heat capacity. And delta T is temperature change either in Kelvin or Celsius. One change in Kelvin is equal to one change in Celsius. Now, if I know how much heat I add to something, and I know its specific heat capacity, I can figure out then, if I know how much I have of it, how much the temperature will change. Or in the case of the water, well, in the water, when we add the cold water to the hot water, the cold water gained energy. It was the energy that the hot water gave up. So they both changed by the same amount of Q. They both had the same amount of heat transfer, just one gained it, one lost it. Now, the specific heat capacity of water is the same, so that didn't change. What did change was the temperature and the mass. So what you could say for this is that the heat that the cold water gained is equal to the heat that the hot water lost. And if I do mc delta T1 equals mc delta T2, well, they have the same heat capacity. So the mass times change in temperature of the first one equals mass times change in temperature of the second, which pretty much means that the one with the higher mass should change by less. The one with the lower mass should change by more. This is actually the equation we could have gotten from our lab, and it actually relates right to here. Now we're going to use this equation to think about if I add two substances together and I know how much they change by, I should be able to figure out how much heat was added. Now, different substances have different heat capacities. Water is 4,186 joules per kilogram degrees Celsius. That's its unit for specific heat capacity, 4,186. Steam is 2,010, and ice is 2,090. So steam and ice are very similar. Water is very high. If you look at a metal like, say, aluminum, aluminum's at 899. Copper's at 387. Glass is even at 837. We see that they're much lower than water, which means that other substances easily change their temperature more easily than water does. Now, sample problem out of your book. How can we use this? A 0.05 kilogram metal bolt is heated to an unknown initial temperature. It is then dropped into a beaker containing 0.15 kilograms of water with an initial temperature of 21 degrees Celsius. The bolt and the water then reach a final temperature of 25 degrees. They end up at the same temperature, which means that the water, it went from 21 degrees Celsius to 25 degrees Celsius. So it gained heat because its temperature went up. The metal, in this case, started at some unknown temperature and dropped down to 25 degrees Celsius. So we don't know how much temperature changed, but we do know that the heat that caused this water to go up is equal to the heat that the bolt had to lose. I mean, if these are the only two things interacting, and the water gained heat, that had to be the heat that the metal lost. Now, the metal, if we know the specific capacity of 899 joules per kilogram degrees Celsius, then we know water has a specific heat capacity of 4,186 joules per kilogram degrees Celsius. Yes, that's a number you're going to know very easily. We can then figure this out. So, mass of the metal, mass of the water, temperature of the water initially. Let's get rid of that. What I tend to think about is you have to think about temperature of water initially and temperature of water final. We know the specific capacity of the metal, specific capacity of the water, and we know the final temperature is 25. We do not know the temperature of the metal initially. So we take these in the calorimeter. You think about the styrofoam cups that we use. It's just the way styrofoam really reduces the flow of heat out or in, so we can contain all the heat within our system. Any of the heat is being transferred. So we have our before, we have our after, and in the after is after all the heat's been transferred. So in this case, again, the heat that the water lost, the water gained, is the heat the metal lost. So if I want to think about the mass, specific capacity, change in temperature of, the water equals the mass of the metal, specific capacity of the metal, change in temperature of the metal. So this equation is set up right here. The heat that one lost is equal to the heat that the other one gained. It has to be this way. That's the law of conservation of energy. So if I look at it this way, I can start plugging in things that I know and things that I don't know. I know the mass of the water is 0.15 kilograms. I know the specific capacity of the water is 4,186 joules per kilogram degrees Celsius. And I know that the water changed by 4 degrees Celsius. It went from 21 to 25. Now, here's actually a little nitpicky thing. Technically, if temperature change is what we're talking about, the degree symbol goes on the other side of the C. If it's just temperature measurement, it goes on the left. Temperature change goes on the right. Don't worry about it too much, but if you ever see it written that way, that's why. Now, this will equal the mass of the metal, which is 0.05 kilograms. The specific heat capacity of the metal, which is 899 joules per kilogram degrees Celsius. And this is the next part, which is kind of easy. The change temperature in here is going to be the temperature of the metal minus 25 degrees Celsius. It went from some higher number down to 25. I don't know what it equals. Now, there's one big equation here and one unknown, which means that I should be able to solve this. It's just simple algebra at this point. Simplify this side to a number. You can simplify this to a number. Then you're going to have to expand this part, get the variable on one side, the numbers on the other side, and solve for it. And pretty much you're going to find a nice little answer that the metal had an initial temperature of 81 degrees Celsius. Now think about that for a second. This piece of metal went from 81 to 25, whereas water only went from 21 to 25. And that's because water has a much higher specific heat capacity, so it takes a lot more energy to change temperature than this piece of metal. Now, some review problems for you to work on. We will go over these in class on Monday. Page 370 problems, they are kind of go over temperature and heat. Page 74 is specific capacity. So these are the problems that are going to be a little bit more intensive. We're also going to do a lab on Monday dealing with specific capacity so we can see the actual measurements. So work on these problems. We'll go over these on Monday.